Yes, the meeting is being recorded. So what are we going to talk about today? We are going to look at some of the elements contained in most element libraries of commercial codes. And we will see how the stiffness matrix and consistent nodal loadings can be determined for several types of elements. We would look a bit at beam elements, and we will rederive the beam matrix for the Euler-Bernoulli beam, but this time using not the direct method as we did in the first lecture, this time using form functions and total potential energy. This is not just a repetition with the aim of showing you that we can obtain the same results. This energetic way at looking at the problem will also give us the opportunity to derive in a simple way not only the stiffness matrix for Euler-Bernoulli beams, but also for what we call Timoshenko beams, which are beams that account for shear deformations. Having done with the beam elements, we will continue with two-dimensional continuum elements. These are surface elements. So here we will need to look at interpolation in two directions, in x direction, then in y direction. We will extend this, we will discuss briefly how we can extend this to three-dimensional continuum elements, the so-called volume elements. And then we will briefly talk about axisymmetric elements. We will not touch upon plate and shell elements, which are the job of Andreas a bit later on during the course. So, if we are talking about beam elements, let's look a bit, recall actually, because you've seen this before, the kinematic assumptions behind beam theory. So how do we assume that the body of the beam deforms? Well, what we assume is that, first and foremost, is that plane section normal to the beam axis stay plane. So the cross section of the beam does not deform. However, this plane section, undeformed plane section, can remain normal to the beam axis after deformation. So the 90-degree angle between the cross section and the tangent to the deformed configuration of the beam is maintained. And this is the classical Euler-Bernoulli beam. We've seen the stiffness matrix of that. Or we can assume that the cross section remains plane, so no deformation, but it's no longer normal to the beam axis after the beam is deformed. This will fall in the category of Timoshenko beams, which account for shear deformation. Why do we say it accounts for shear deformation? Well, because the angle between the cross section and the beam axis will change. The change in angle implies a shear strain. This is the one changing the angles, the shear strains. So Euler-Bernoulli, no shear strains. Timoshenko beam, shear strains are accounted for. Now, if we start with the Euler-Bernoulli beam, we would think, and we are looking just at the bending part, because as we've seen in the first lecture, the axial part is already solved. It's strictly independent of the bending effect, so we can focus now on the bending part of the stiffness matrix. Since we have an Euler-Bernoulli theory, so cross-section stays plane and orthogonal to the deformed beam axis, this actually means that the rotation of the cross-section theta is equal to the first derivative of the displacement v. This is classical. So dv dx, or in shorthand notation, v v comma x is equal to theta. What does this tell us? This tells us that we only need to interpolate for v, because once we have approximated v through our interpolation function, then theta will simply be at our disposal through differentiation. So we have v of x, which can be expressed as n1 of x times v1 plus n2 of x times theta 1 plus n3 of x v2 plus n4 of x theta 2. So now the interpolation of v contains not just v at the nodes, but also theta 1 and theta 2, which are the derivatives of v at the two nodes. Having involved the derivatives of v into the formulation, what we can say is that we have now 4 condition equations to determine the shape functions. So we will be allowed to use a polynomial which has 4 constants in its definition, and that would be a 3rd-degree polynomial. a0 plus a1x plus a2x squared plus a3 x raised to the power 3. And then we will determine the unknown coefficients in each shape functions simply by taking into account the boundary condition. So n1 of x should have value equal to 1 for x equal to 0. Its first derivative at x equal to 0, which is theta 1, should also be 0. N1 of L at the other end, at node 2, should be equal to 0, because v2 should be equal to 0. And the first derivative of n1 evaluated for x equal to L, so evaluated at the second node, should also be 0. Our 4 constants, which will give us n1 of x as shown here in the slide. We will repeat this procedure for n2, which involves theta 1, for n3, which involves v2, and for n4, which involves theta 2. And for each of these shape functions, we will determine the constants in the 3rd order polynomial that we use as a general expression for the interpolation functions. Okay, having said that, let's look at the expression of the strain energy and of the stiffness matrix. The strain energy, please note that we only have one strain component, which is epsilon x. So the strain energy would be half the integral over the volume of the beam of E epsilon x squared dV. If we perform the integral over the cross-section area, then what we will obtain is the second order of the second moment of inertia of the beam, I. So this is equal to 1/2 an integral from 0 to L, so over the length of the element, of EI, E Young's modulus, I second moment of inertia, times d2v dx2 squared. d2v dx2 squared is what is called the curvature. And as the expression on the slide suggests, it plays the role of a strain measure. So instead of working with epsilon, we will continue to work with a curvature and say the curvature is now our strain measure. How do we compute this? Well, very simple, giving the way in which we have interpolated V. So d2v dx2 or vxx is second derivative of n1 with respect to x times v1 plus second derivative of n2 with respect to x times theta 1, and so on for v2 and for theta 2. We can also write this in a matrix form, and we now have the matrix B, the strain displacement matrix, times the displacement at the nodes, v1, theta 1, v2, theta 2, whose product will give us the curvature at any point within the B. The matrix B is very easy to compute. We have n1, n2, n3, n4 as third degrees polynomial. So we just have to differentiate twice these third degree polynomials with respect to x. And what we obtain is the vector shown here on the slide, 12x over L3 minus x over L squared, 6x over L squared minus 4 over L, and so on and so forth. As you see, now the matrix B is no longer constant, it's a function of x. We can then use this expression of the matrix B to compute the strain energy, and so we simply replace Vxx squared by B times D squared, and what we obtain is 1 over 2, an integral over the length of D transposed B transpose times EI. These are Young's modulus and second moment of inertia times B times D, and of course dx. So recognizing the fact that D is independent of x, so it gets outside the integration, what we are left with is 1 over 2 D transpose times K, stiffness matrix, times D. And the stiffness matrix is simply the integral over the length of the product B transpose EI times B. And if you perform this integral, which actually amounts to integrating second order polynomials, so you actually perform the matrix multiplication and then you integrate term by term from 0 to L. We have 16 second order polynomials to integrate from 0 to L, but these are relatively easy performed. What we end up with is the expression that we already know. We have obtained it through direct equilibrium reasoning during the first lecture. Once again, I would like to stress the physical significance of a column in this stiffness matrix. These are the forces that I need to apply to the beam in order to maintain a particular deformed shape. In case this is the first column I am talking about, then that particular deformed shape is one with V1 equal to 1, then theta 1 equals to 0, no rotation, and then at node 2, V2 equal 2, and theta 2 also equal, equal to 0, and theta 2 also equal to 0, so no rotation at the second node either. So keep this in mind. This is valid for all finite elements that we are deriving in this way. Now, if we want to put the axial degrees of freedom, we just add the stiffness matrix for the bar element at a certain location. We can either spread it, or we can assume that U1 and U2 are the first 2 degrees of freedom, and then V1 theta 1, V2 theta 2. These are different way of organizing the stiffness matrix. They are related to the order into which we assume that the nodal freedoms are placed in the nodal displacement plane. Once again, remember axial and bending effects for this type of beam, a straight beam, are not coupled. Having said that, let's stop 1 second for some questions. So this is the opportunity for you to ask questions.
Yeah, yes, I would like to ask a question.
Yes.
In the last lecture, the B matrix was the first derivative of the shape functions.
Yes.
M.
Yeah.
And now it is the second derivative. So I understand that it has to do with curvature and.
Yes.
But what is it in the? Because I don't really remember. What was it in the last lecture when we just had a bar and we had the first derivative of.
Yes.
M and X, if you compare that.
Let's talk about the bar element. So for the bar element, epsilon x was the first derivative of the axial displacement. Yeah.
Yep.
So if we knew u of x, say, we could differentiate it once, and that was our epsilon. Yeah.
Yeah.
Well, for the beam, we have a more complicated kinematics. Do you see the picture?
Yeah.
Yeah. For the beam, we have a more complex kinematics. We have V, which is the bending displacement of the beam axis. And because the cross-section is rotating, at each point along the cross-section, we will also have an axial displacement, which is as shown in the slide, minus y times theta, the rotation of the cross-section. Yeah?
Mm-hmm. Mm-hmm.
So now we have epsilon x, which is minus y times d theta dx, and we have gamma xy, which is dv dx minus theta, in case we want to account for shear deformation. So if we have the Euler-Bernoulli assumption, so no shear strains, that means dv dx is equal to theta and gamma is equal to 0. But epsilon still involves the bending displacement. It still involves d theta dx. Now, if dv dx is equal to theta, then the theta dx will be the second derivative of v, isn't it?
Mm.
So your epsilon x will be, for an Euler-Bernoulli beam, will be minus y d2v dx2. Do you agree with me?
Yeah, I see it. Yeah.
So all of a sudden, we have the second order derivatives there, which are required to define epsilon for bending. We are no longer in a situation where we could use just the first derivatives of the axial displacement. We will need to use the first derivative of the rotation, that is for the Euler-Bernoulli beam, the second derivative of the bending displacement v. And that is why we will move from the first derivative to the second derivative, because epsilon x will be minus y d2v dx2. And if I replace this expression minus y d2v dx2 here, and then I integrate over the area, the term y squared times dA will give me the second moment of inertia, and then I'm left with d2v dx2 squared, which is the second derivative of v.
Okay.
Is it a bit more clear?
Yeah, it is. So just so I have understand it correctly, so when you have a bar element, it's always the first derivative of the shape
Yes.
function.
Yes.
And in a beam element, it's always the second derivative.
Not always. For
okay.
Euler-Bernoulli beams.
Oh, okay, okay, yeah.
We will move to Timoshenko beams, which are a bit more complicated.
Okay.
So in the case of the Euler-Bernoulli beams, this is what we have.
Okay.
And this comes from the fact, the second order derivative comes from the fact that the first derivative of v is equal to theta, by definition. By the fact that we have imposed a zero shear strain. If we don't impose a zero shear strain, then dv dx is no longer theta, it's different. But if we stay with the Euler-Bernoulli theory, then dv dx is equal to theta, and then we get in the strain energy, we get the second derivative of v. Yes?
Yep. Yep.
Other questions?
Questions.
Yeah.
In the page of strain energy and the stiffness matrix, yes, it's this page, and in the final line, yes, this page.
Is this the page?
No, the previous one.
This?
Yeah, yes. In the last line, we can see that U equals to this formula, and it's v comma xx square.
Yeah.
But why do you times the transpose matrix of D and B before EI?
Yes, because this is, if I want to express Vxx squared as a in matrix form, B times D, then the squared will result in this expression, D transpose B transpose times BD.
So it means the transpose matrix of D and B equals to B and D, right?
The transpose, so if I transpose a matrix product, 8 times B transposed, then the results would be B transposed times E transposed. So this is the thing that has to do with the rules of linear algebra and matrix algebra.
Yeah, I understand that.
So A times B, if I make the product and transpose it, it's equal to B transposed times A transposed. So B times D transposed will become D transposed times B transposed.
Okay, so D and B will be the normal matrix.
Yes.
Okay, understand.
So you have your B and D matrix and you simply transpose them.
Yeah, okay, understand.
Other questions? If there are no more questions, then I think I will again close your microphones and continue. And this time we will move to Timoshenko beams. Now, as we've seen in the previous slide, if these are the two strain components for a beam element, epsilon x and gamma xy, Euler-Bernoulli meant gamma xy equal to 0, that is dv dx equal to theta. However, Timoshenko theory says gamma of x and y is not equal to 0. There is a shear strain there. The shear strain that is changing the angle between the deformed beam axis and the cross section. And which actually means that dv dx is no longer equal to theta. Actually, the difference between these two terms will give you the shear strains. So what do we do now? What do we do now? But before we talk about this, let's look a bit at the Bernoulli-Euler theory and rederive the expression of the consistent nodal loadings. I'm sorry, I've skipped this slide. These will come from the potential of external forces, which in this case, assuming Q is directed normally to the beam axis, will be Q times V of x dx, an integral from 0 to L, Q V of x dx. We simply replace V of x by the approximation given by the interpolation functions, and we have Q times N1 of x V1 plus Q times N2 of x theta 1, Q times N3 of x V2, and Q times N4 of x theta 2. The first term here will give us V1, the vertical force at node 1, which is Q times N1 of x dx. And if we perform the integral, it will give us the value QL over 2. This is what we knew. The moment involved in the consistent nodal loadings would be Qn2 of x dx. It's normal because the moment energetically is consistent with the rotation theta 1. And performing the integral, since we know N2 of x, it's a third order polynomial, we can integrate it. If we perform the integral, it's QL square over 12. Then we move at the other end. V2 will be Qn3 of x dx, and that will give us QL over 2. And M2 would be Qn4 of x dx, which will give us minus QL squared over 12. These are exactly the expression that we derived in the first lecture through direct equilibrium arguments. These are the consistent nodal loadings. Once again, what you should recall here is the idea that consistent nodal loadings are both statically equivalent and energetically equivalent to the applied distributed force. So here is the energy equivalence, if you want. The work done by the load Q through the displacement V over the length is equal to the work done by the consistent nodal loading through the nodal displacement. So very important, the energetic equivalence is also maintained, not just the static one. Okay, having corrected this omission from the lecture, let's look at Timoshenko beams. We said that in this case, dV dx, or Vx in V, x in shorthand notation, is no longer equal to theta. What does this mean from a practical point of view, from the point of view of the interpolations? Well, what this means is that we will have to interpolate separately the two quantities. So we will have to interpolate separately V of x, and then we will have to interpolate also theta of x. There is no connection between the two. dV dx is not theta of x. So now, at each node, we only have two conditions. At each node, we only have one condition instead of two, which will mean that N1 of x and N2 of x cannot be anything else than linear functions. N of x would be 1 minus x over L, and N2 of x will be x over L. The same form functions can be used for theta. So N1 of x V1, N2 of x V2, theta x, N1 of x theta 1, N2 of x theta 2. Once again, This happens because instead of 2 conditions at each node, we only have 1. So V of 0 should be equal to 1, V of L should be equal to 0. That will give us just 2 conditions, meaning the best thing we can do is construct a first order polynomial, a plus bx, because we will have enough equations to determine the 2 constants, and a and b. The strain energy will be an integral from 0 to L of EI times d theta dx squared plus GA dV dx minus theta squared. This one comes from epsilon x. This one is gamma xy, the shear strain. And now you see that we have the shear modulus, which comes into play because this is the shear strain we need to compute the energy associated with the shear strains. So EI for the bending part, GA for the shear strain energy. And that will give us the matrix K. How will it give us? Well, in a very simple manner. We replace d theta dx with a value which comes from here. So we differentiate n1 and n2 and compute the B matrix and have this term. Then dV dx, we differentiate this and subtract theta of x, which is theta, which is this. So this is rather direct algebra to determine the stiffness matrix. There is something else which I wanted to point out to you, because these Timoshenko beams might have a defect which might completely destroy your results at the end of the day. If we look at the 2 terms in the strain energy, we see that one is associated with bending, d theta dx, whereas one is associated with shear. Let's call them U bending, U from bending, and U from US, U from shear. Assume now that we have a rectangular section, that the cross section of our beam is rectangular. So it's B times H, where H is the height of the beam. Assume also that the beam is very slender. So the height to length ratio is very small. This happens for slender beams, slender columns. In this case, we will expect the Bernoulli hypothesis to be fulfilled, at least in the limit. So we will expect gamma xy, which is dV dx minus theta, to go towards 0, such that the shear strain energy, which is GA over EI times dV dx minus theta squared, should also tend to 0. This is a very slender beam. The shear strain effects are negligible. That's why Bernoulli proposed his hypothesis. So the part related in the strain energy, the part related to the shear strain, should become gradually, as H increases, should become smaller and smaller and smaller, should tend to 0. Now let's look at this ratio here, which actually governs the value of the strain energy. This is GA over EI. If we assume cross-section of dimensions B and H, then this ratio is 12G over E divided also by H squared, so the height squared. Now, if H is very small, and the smaller the H becomes, then the larger this ratio will become. If this is 0, 1 squared, it's 0, 0, 1. By division, you will get 12g over E times 100. If it's even smaller than 0, 1, if it's 0, 0, 1, then we will multiply 12g over E with 10,000. What does this mean practically? This means that in order for the shear strain to tend to 0 as H decreases, this condition should be very accurately enforced. So dV dx minus theta should also plunge towards 0. If this doesn't happen, then the shear strain will become much larger than the bending strain, simply because this vanishingly small, or this shear strain, which should be vanishingly small, it's not, and it's multiplied by a very large constant here, Ga over Ei. So we are depending on how well we can enforce this condition in the limit. Now, how well can we enforce this condition? Well, this condition is actually enforced in our finite element by our approximation. V of x is this, theta of x is this. If we have a linear approximation, we will have a rather poor approximation here. So the condition will not be actually very accurately enforced. Then this will happen. The shear strain energy will be much larger than the bending energy, and the element will actually lock. You will take smaller and smaller heights, and the displacement that you compute using your finite element mesh will be smaller and smaller. At a certain point, they will tend to 0. This is what is normally called locking of an element, and comes from the fact that instead of having the bending strain energy dominate, we will have the shear strain energy dominating. This one should be 0. And it's not. It's not, because we enforce this condition, dV dx minus theta tending to 0. We enforce it poorly. Our approximation is rather poor, and we multiply this error by a very, very large constant. Now, the reason for which I'm discussing this at this particular point is the fact that some commercial codes, there are ways of correcting this. And some commercial codes have beam elements which have this locking remedied. Some of them do not. So whenever you use a Timoshenko beam in a computer code, look at the manual, the theoretical manual of the program, and see if they deal with the shear locking issues for the Timoshenko beams. If they do not deal with that, then use Timoshenko beams just for, say, rather high beam. So use Timoshenko beams for H over L, which is, say, higher than 0, 1. Now, quickly, a comparison between Timoshenko and Euler-Bernoulli beams. If you compute this, height 4 meters, length 20 meters, by Timoshenko theory and by Euler-Bernoulli theory, so Timoshenko beams, Euler-Bernoulli beams, what you will get in displacement difference is about 10%. So the Euler-Bernoulli beam would be about 10% stiffer than the Timoshenko beam. Actually, for L over H you shouldn't bother about Timoshenko and Euler-Bernoulli unless your L over H is less than, say, 10. So from heights equal to 2 meters and upwards for this length, then I would need to bother about difference between Timoshenko and Euler-Bernoulli. Otherwise, the errors will be a couple of percent, and there is no problem with that. Before taking a break, let's discuss 2D beam elements versus 3D beam elements. The 2D beam elements, the ones that we have discussing, have 3 degrees of freedom at each node. So 1 axial displacement, 1 vertical displacement, and a rotation theta. If we have 3D beam elements, the only thing, the extension is rather trivial. We simply add bending effects in another plane. So at node 1, we will have an extra displacement here and an extra rotation. And then we will also have torsional effects. So rotations around the beam axis at 1 and 2. The good thing about torsional effects is that they are totally uncoupled from axial force and bending effects. So we will be able to, it's very simple to derive the matrix. It's very similar derivation to the axial effects. We will have a 2x2 stiffness matrix, which we will simply assemble together with the bending and the axial effect stiffness matrices. So the extension is rather trivial. You will find it in, if you want more details about that, you will find them in the book. Okay, having said that, let's unmute everybody and listen to some questions. Do you have questions?
I have a question.
Yes.
Do you hear me? Yeah.
Yes, of course.
You said that for the Timoshenko beams, we use linear V and theta,
Yeah.
because we only have one condition at each node.
Yes.
But that's just a model. That's not the reality.
Of course.
Right. Okay.
So this is an approximation of V, and this is an approximation of theta.
Yes.
Yeah. This is the best approximation that we can produce, given the fact that we have 2 values, V1 and V2 for V, and we have 2 values, theta1 and theta2 for
Yes.
theta. The only thing that we can do is linearly interpolate between these 2 values.
Yes, because otherwise we don't have enough.
We don't have enough conditions.
Yep.
And you are very right. This is an approximation. It's not such a great approximation either.
No. So could we say that the Euler-Bernoulli is like we have a better approximation given the.
In some sense, yes.
Yes. Okay.
But in another sense, no.
No, because then we don't consider the shear strength.
Exactly. So we need to be very careful here. Yes, the approximation is much better. But
Okay.
For certain problems, the basic assumptions might be worse.
Mm-hmm.
Do
Yes, I see.
Do you get my point here?
Yes.
So I'm doing a better approximation, but I might be doing them from a worse initial assumption.
Yes.
Which might reflect at the end of the day. At the end of the day, might reflect on the results here.
The results.
So I have a Timoshenko theory telling me the displacement should be 10% higher for the Timoshenko than for the Euler-Bernoulli. And this comes from the initial assumption, no shear strains.
Yes, yeah, I see, I understand.
Yeah. Okay, other questions? That was a very good question, actually. Other questions?
I have one. I don't know if you can hear me.
Yes.
Thank you. I'm not sure if I catch it or understood well the concept of locking, but if is it true that I can like detect locking if I keep a constant load and diminish the h, the height of the cross section?
Yeah.
The deflection will get smaller instead of larger?
Yes, this will, if the element locks, and if you have a low height, it's very, if you make a test on a Timoshenko beam, which doesn't have this locking issue resolved, then what will happen is, let's say you start with an L over H equal to 5, and you will get a displacement. And then you'll maintain the L and you'll reduce the height. Say you'll reduce it by a factor 10. So you'll have L over H equal to 50. Then you'll redo the analysis and you will end up with a corresponding much larger displacement than in the first case.
Yes, sure.
Of course, because you have less bending stiffness.
and the constant loading we're talking about.
And then you move and say, okay, L over H is now 500. And then you all of a sudden see that L over H equal to 5,000 will give you a displacement which is much smaller than what you got for L over H equal to 5.
Okay, I understand.
So, and then you say, okay, what's happening here? I maintain the load, I maintain the length, I should have a much larger displacement because my H, my second moment of inertia, is reducing substantially. And instead, I get a much smaller value.
Okay, yeah, doesn't make any sense.
And it doesn't make any sense. And then the question is, why does this happen?
I understand now.
Because a very slender beam should store its strain energy mostly in bending. The amount of shear energy that you are storing in as shear strain energy should be vanishingly small as H diminishes.
Okay.
Well, this doesn't happen because you are approximating poorly the V and the theta. So this will not actually work for the approximations that you have chosen. And you will have locking. And this is how you detect it. You take a simply supported beam, you load it by a concentrated force at the middle or by a uniformly distributed force. You maintain the force, you maintain the span, the length of the beam, and you gradually reduce H. If what you obtain is reasonable, so the displacement growing bigger and bigger as H is reduced, then your beam works properly and the locking effect has been dealt with. If you see that starting at some L over H ratio, you start to have less displacement than in previous cases, then you have a problem. Then you have a locking problem. Normally, in all theoretical manual of the commercial codes, you will see some reference to locking. If not, if you don't see and they don't discuss it, then use Timoshenko beam theory just for stocky beams, just for beams with, say, L/H less than 10, and then Euler-Bernoulli for the rest of them, because then you might have problems with shear locking.
Perfect. Thank you.
Is it more clear now?
Yeah, it was clear. It was perfect.
Okay. Other questions? If there are no more questions, then let's take a 10 minutes break, fill our coffee cups, and reconvene at 25 past 10. Is this agreeable with you?
Yep.
Okay, then we go for this. Yes. Now, let's continue, and this time let's forget about beams and move on to continuum elements. And we will be talking about two-dimensional continuum elements, plane stress and plane strain elements, briefly about axisymmetric elements and 3D continuum elements. This is a bit different from trusses and beams in the sense that the continuum elements, if they are in 2D, they are surface elements, so we will need to approximate our displacement this time in both x and y. And if they are 3D continuum elements, they are volume elements, so the element will have a physical volume. It will not be an axis or so a line or a surface. It will be a volume, and we will need interpolation in 3 directions, x, y, and theta. But let's start with the plane stress elements and plane strain elements, the continuum elements, and then look at a small problem that we used in the previous lecture too. And the idea is that we want a solution for this particular cantilever structure, which is shown on the slide, given the h/L ratio, so the height of the cantilever is comparable to its span. We wouldn't expect this to behave like a beam. And we will need to go to a plane stress solution. A plane stress solution which will involve epsilon x, epsilon y, gamma xy, so this time 3 strain components, and which will involve sigma x, sigma y, and tau xy, so 3 stress components. Now, what we should realize here that if we want a complete solution for this problem, what we need to determine is the displacement field. So the 2 components of the displacement vector u, which is u, of course, a function of x and y, a function of x and y, and v, also a function of x and y. Why is that? Because once the displacements are known, the rest will simply follow. If I know u and v, then epsilon x is du dx, epsilon y is dv dy, gamma xy is du dy plus dv dx. Or d dx 0, 0 d dy, d dy d dx, which is the differential operator applied to the vector containing the two displacements, u of x and y and v of x and y. So we can actually write this in a matrix form, condensed way, a differential operator, which is this one, and multiplied by, applied to a vector u. Once we have epsilon, then of course, using the constitutive matrix for plane stress problems, which is shown here, we can get the stresses. So E times epsilon is sigma x, sigma y, tau xy equals to E, this matrix here, times epsilon x, epsilon y, gamma xy. We no longer have just one constant, the E modulus. We are also dealing with Poisson's coefficient, and the matrix E, as I said, for plane stress problem looks like this. Now, what do we have at our disposal? Well, we have some differential equations of equilibrium combined with some compatibility conditions, and of course combined with boundary conditions. These are conditions that our solution will have to fulfill on the boundary. And I would like to remind you that we have two types of boundary conditions. The so-called essential boundary conditions, these are expressed directly in terms of the displacement, which are at the clamped edge of the left side of the cantilever. And we have natural or non-essential boundary conditions, which are expressed in terms of stresses, that is essentially derivatives of the displacement. So essential boundary condition, natural or non-essential boundary conditions. Now, the solution to our problem is obvious, given our finite element philosophy. We divide the continuum into elements which are connected at nodal points, just as shown here on the slide. So we will divide this surface into smaller surfaces, which are our elements, and we will assume that these elements are connected at the nodal points. At each node, say node I, we have two displacement components, u of I, the horizontal, and v of I, the vertical. And the main idea in constructing the stiffness matrix is the same as before. Within an element, we do not know how u and v will vary. So we don't actually know u of x and y and v of x and y. But for each element, starting with its nodal displacements, we can construct an approximation using known functions and the nodal displacements. These known functions are what we have called, until now, form functions. We will maintain this name. So known functions, form functions, and nodal displacement. This is the way in which we construct an approximation for the displacements inside a finite element. Then we use the principle of stationary total potential energy to express the equilibrium of each element and determine the stiffness matrix K. This is totally, this is agreeing in all details with the general procedure that we have introduced last lecture. Now, how does our interpolation look like? Assume that our smaller parts are triangles. Then u of x and y inside my triangle will be n1 of x and y times u1 plus n2 of x and y times u2 plus n3 of x and y times u3. The three horizontal displacement at u1, u2, and u3. And we can use the same form functions, n1, n2, n3, to interpolate v. So v of x and y for the triangular element will be n1 of x and y times v1 plus n2 of x and y v2 plus n3 of x and y times v3. The n1 to n3 are known functions of x and y that we call shape functions. Of course, if we add one more element, one more node, and make this a rectangle instead of a triangle, we will add up a fourth form function, n4, which will multiply u4, the horizontal displacement at the fourth node. The same for v. n4 will multiply this time v4. So actually, for both these elements, we can write symbolically u of x and y is a sum from 1 to the number of nodes of ni of x and y times ui. V is the sum from 1 to number of nodes ni of x and y times vi. This is what we can do for a 3-noded or a 4-noded element. One remark here. U and V are assumed to be independent of each other. So there is no connection between the U's, the horizontal displacements, and the vertical displacement. This will allow us actually to use the same form function. Why do we use the same form function? Why not use different form functions for U and different form functions for V? Simply because we do not actually know these are interpolations in the element local coordinate system. For instance, with the origo at node 1, with the x-axis from node 1 to node 2, and the y-axis orthogonal to the x-axis. These are interpolation in a local coordinate system. We do not know in the global system how this element will be oriented. So doing different type of interpolation, different type of approximation for U and V, we might end up with a situation in which we favor one displacement over the other, and we have no control on how these elements will be arranged in the final mesh. So this is why we use absolutely the same interpolation for U and for V. The only difference will come from the displacement that the form functions are multiplied with. Now, how do we choose our form functions? The general conditions for, let's say we assume that we have a 4-noded element. Now, in order to determine the coefficients in the form function, in a particular form function, say at n1, the one that will be involving u1 and, of course, v1 if we interpolate v. What are the conditions that we need to impose for n1? Well, n1 should be equal to 1 for x equal to x1 and y equal to y1. So if I evaluate n1 at node 1, then I should get the value 1. Because the condition is this one. U of x1 and y1, which is the sum of form function time respective displacement, should be equal to 1 u1. So n1 of x1 and y1 should be equal to 1. Okay, what happens with the value of n1 at the other nodes, at node 2, at node 3, and at node 4? It should be equal to 0. Simply because the displacement at node 2, say u of x2 and y2, should be equal to u2, so no u1, That means n1 must necessarily be 0 for x equal x2, y equal y2, that is at node 2. And this is the general way in which we determine any ni. Ni should be equal, corresponding to a node I. Ni should be equal to 1 at node I and 0 at the rest of the nodes. We have 4 nodes. Then we can assume that in our N1, in our approximation, we can have 4 constants. Now, these 4 constants refer to a polynomial in both the x and y, because we need to establish an approximation which will involve both coordinates, both x and y. So the only thing that we can do here is a plus bx plus cy plus dxy. That's the only alternative that we have at our disposal, because we just have 4 conditions here. Then 4 constants is all we can do, the only thing we can do. Now, I think we will stop a bit and listen if there are any questions. Okay, now your mics are on. Do you have any questions? Yes, I'm listening. Come on, we need a brave soul to ask the first question. If there are no questions, then let's proceed. Now, are there any conditions? Are there any things that we need to respect when we construct our approximation? You've seen that we are very much focused on using polynomials. Are there any conditions that we need to place on these interpolation functions? And it turns out that we have. One condition is that no cracks or overlaps should appear between the edges of 2 adjacent elements. So if we have this situation, the edge 2, 3 is common to both element 1 and element 2. So we will construct an approximation of the displacement along edge 2, 3. We can construct it using element 1, and we can construct another one using element 2. What we need to make sure is that the approximations from both elements coincide. We have no overlaps and no cracks developing. Why do we need to impose such a condition? Well, we need to impose such a condition because we are using the total potential energy and the theorem of the minimum total potential energy, and the statement of that energy principle was that for all admissible variations or all admissible deformed configurations of the structure, and the condition for a deformed configuration to be admissible was that the compatibility conditions should have been respected. And they were exactly this: no cracks and no overlaps within our structure. So this comes directly from the conditions expressed in the principle of total potential energy. We cannot allow this situation. This will violate the condition for the total potential, minimum of total potential energy. So what this means is that the approximated fields U and V must be at least C0 continuous over the element edge. So over the element edge, we need to have continuity in both U and V. This is C0 continuity. We require continuity of the function itself. However, we do not require continuity of the derivatives. So we can accept such a situation. The slope of either U and V will be different from element 1 to element 2, which actually mean that in du dx we will have a discontinuity. We've already seen that and the effects of that when we talked about bar elements. The strain and stress field over the element edge will not be continuous, but the displacement will. Okay. How do we determine the stiffness matrix? Well, we simply apply the same procedure as we did for the same procedure that we applied for the bars and the beam elements. We approximate the displacement field as n matrix of shape functions multiplied by the vector d of nodal displacement. U is, of course, it contains the two displacement components, which are both function of x and y. And then is the matrix of the shape function, while D is the matrix containing the nodal displacement. Thus, for the four-noded element, for example, we will have n, this time 2 rows, 8 columns. N would look like n1, 0, n2, 0, n3 of x and y, 0, n4 of x and y, and 0. This one multiplied with the vector d, which is u1, v1, u2, v2, u3, v3, u4, v4, will give us u of x and y equal to n1, u1, plus n2, u2, plus n3, u3, plus n4, u4. We move this one step ahead, and we will have for v, the second row, 0, n1, 0, n2, 0, n3, 0, n4. So this is n. As yet, we have not defined the n1 to n4. This is n. The strains are evaluated by applying the differential operator u, delta on the vector of displacements u. So epsilon x du dx dv dy du dy plus dv dx. Here we can stop and replace u by our approximation, which is n times d. D is constant, so we will apply our differential operator, which is this one, onto the matrix of shape functions. And doing this, so actually differentiating with respect to x, to y, and to summing up the differential with respect to y and x, we will determine the B matrix, the strain displacement matrix, the matrix that gives you the connection between the nodal displacement and the strains within the element. Once we have done this, we look at the expression of the strain energy, we replace epsilon by B times vector of nodal displacement, and we get the expression of our stiffness matrix, which is an integral over the element's volume, B transpose EB. Now, B is a matrix, is no longer a vector. E is the elasticity matrix, a matrix, not just a value of Young's modulus. And this we will have to integrate over the length and over the thickness. So we will have to integrate over the volume of the whole element. And here you will have the expression of the potential of external forces. This is valid for the volume forces. D transpose N transpose is simply the approximation of U transposed. And this is valid, a term which is valid for loads applied at the edges of the element. What we obtain at the end of the day is total tension 1 over 2 D transpose KD minus D transpose times RE, vector of consistent nodal loadings, which gives us the equilibrium K times D minus RE is equal to 0. So conceptually, no difference from bar elements and beam elements. It's just that the expression now starts to become a bit more complicated. Actually, this formula for the stiffness matrix of one element, if we are talking linear elements, displacement-based linear elements, this is the general formula. Whatever element we might look at, what we need to do is determine the B matrix, actually computed from the shape functions, and then integrate this matrix product over the volume of the element. If we make sure that in the shape functions matrix, so in N, matrix containing shape functions, if we make sure that we have functions which are easy to handle, for instance, polynomials, then we will be able to integrate this without too much trouble. Sometimes analytically, if not numerically, we'll see that a bit further on during the course, but we will be able to compute this integral, which actually means that we perform the matrix multiplication and then in the result, we integrate term for term. The consistent nodal loadings is this one. Forces, volume forces here, and tractions applied on the edge. This is what I mean with tractions applied on the edge. I have my phi of y, which is applied along the edge 4, 3, or my phi of x, which is applied along the edge 1, 4. Whereas the volume forces are applied at all points within the surface of the element. We have an fx and fy. We will multiply with the corresponding displacement and integrate over the volume. Here we will integrate over the length of the edge. Okay, now, and this is very important. Now, can we choose any sort of interpolation functions, any sort of polynomial, given that we can determine all the constant? Can we use anything to approximate the displacement. And then it turns out that there are some conditions that the form functions need to fulfill. And these conditions are the one given on the slide. First of all, if we assume that the expression of the potential energy contains derivatives of order m of the displacement. In our case, for the plane stress problem, they contain derivatives of first order. So the expression of the strain energy contains epsilon x, which in this case is du dx dv dy. So if the total potential contains derivatives of order m of the displacement, then within each element, the interpolation must contain a complete polynomial of order m. For the plane stress problem, as well as for the plane strain problem, this means that the interpolation for both u and v must contain a complete polynomial of first degree. By a complete polynomial, I mean a0 plus a1 of x plus a2 of y. That is complete in both x and y. These are all the first order terms in a polynomial in x and y. Of course, the same is valid for v. Across the boundaries of the element, the approximation must be c m minus 1, which actually means, that's a mathematical way of saying that the function itself, the approximated field, field variable, and its derivatives up to order m minus 1 must be continuous. So for plane stress problem, which contains derivatives of first order, this means that the problem has to be Cm minus 1, that is C0 continuous. So we need C0 continuity for the plane stress problem. We need this C0 continuity. The function is continuous, but the first derivative not necessarily. If we would have had, say, second order derivatives in the expression of the total potential, then we would have required a polynomial of order 2, and we would have required C1 continuity. That is, both u and v and their first derivatives should be continuous. This will be the case for some plate and shell elements. Then there is something which is related to how conditions which are related to how the element responds to rigid body motions. The form functions should be chosen in such a way that the element can undergo rigid body motions without developing strains. And furthermore, the element should be able to reproduce exactly states of uniform strain. Why do we require these ones? This one? Well, of course, this is obvious. We don't want an element that will develop stresses under rigid body motions, because that will be, if we will rigidly translate an element long enough, we will develop enormous stresses if the element is not able to represent correctly rigid body motions without developing strains. Why do we need states of uniform strain? This follows from, say, the following reasoning. The finite element is approximate And as we take more finite elements, we will reduce the error that the numerical approximate solution is giving us. What happens in the limit? So assume that we take a lot of elements, very, very small elements. Then the elements themselves will be so small that the state of strain will be almost constant within the element, simply because the domain of the element is so small that the strains will not have the time to vary too much from one point to another. That is, in the limit, we will have very, very small elements, all of them in states of uniform strain. So as long as we can reproduce states of uniform strain exactly, then our elements will converge to the correct solution. So this is the reasoning behind this requirement. Then we have additional requirements. For instance, we would like to have balance in X and Y. So my choice here will be A plus BX plus CY plus D times X times Y. I will not choose D times X squared. I will not choose D times Y squared, because that will generate an unbalance in the way in which I look at the two directions. And this might not be beneficial to the solution. So balance in X and Y, the next term that I have here should be A3 times X times Y, to keep the balance between the two directions. Having said that, let's stop very quickly for some questions.
Okay, I would like to ask about the slide we are looking at right now.
Yes.
That u and x, u of x and y equals 1 x, y, a1, a2, a3. Is 1 x and y, is that a shape function? I mean, is that...
No, this is a vector. So u of x and y,
yeah,
is a1 plus a2 times x plus a3 times y.
Okay, but
This is the vectorial form of writing a second order, first order polynomial in x and y.
Yeah, but I just wonder, how is this thing that we are looking at, how is that related to the shape function? And
for the particular, to be frank, that was the next slide I was going to talk about.
Oh, okay, okay. Because I just looked at it and I thought, like, u is
now,
equal to n.
For the triangular element, we don't even need to go through shape functions.
Oh, okay, okay.
Because it's so simple.
Oh, okay.
So we will not use shape functions. The only thing that I wanted to point out here is that u and v are both first order polynomials in x and y.
Mm-hmm. Okay.
The other questions? If there are no more questions at this moment, let's continue. And look at triangular element. So u of x and y is simply a1 plus a2 of x plus a3 of y. V of x and y is a4 plus a5 of x plus a6 of y. linear displacements, so displacements which are linear in both x and y, will lead to constant strains. And this is why this element is called the constant strain triangle. It has constant strains. Epsilon x is du dx, so epsilon x will be equal to A2. Epsilon y is dv dy, so epsilon y will be equal to A6. And gamma xy is du dy plus dv dx, which actually means A3 plus A5. These are how the strains look like. They are constant. How do we determine the constants A1 to A6? Let's look first at A1 to A3. We know that u, if we choose the origo of the coordinate system at node 1, with the x-axis going from 1 to 2 and the y-axis orthogonal, then u of 0 and 0, so u at node 1 should be equal to u1. U at node 2, so u of x2 and 0 should be equal to u2. U of x3 and y3, so here at node 3, should be equal to u3. We have three equations. We have three constants, a1 to a3. So what we have is that a1 should be equal to u1. A2 should be equal, if we solve this system, you can do it by hand to check that I'm not lying here. If A2 would be minus 1 over x2 u1 plus 1 over x2 u2, A3 will have this expression involving coordinates at the nodes and the three displacements, u1, u2, and u3. These are A1, A2, and A3. We did absolutely the same thing for V, and we get the expression for A4, A5, and A6. You will see that they are extremely similar. The only thing different, which differ here, is the displacement with which these coefficients are multiplied. Now, we know that epsilon x is equal to A2, epsilon y A6, gamma xy is A3 plus A5. So we simply replace this expression in epsilon x, epsilon y, gamma xy, and we get our B matrix, which multiplied by the values of the nodal displacement will give us epsilon x, epsilon y, gamma xy. Of course, these are constant because this matrix, the B matrix, is constant, simply because the interpolation of u and v is linear. So by differentiation, we get constant strains. The stiffness matrix, we've seen the generalized formula, an integral over v, B transpose times E times B dV. Finally, since all these terms are constant, this product gets outside the integral, and we have an integral over the volume from dV. So this integral will give us the volume of the element, which is the area of the element times the thickness times the product B transpose times E times B. B is this. E, we've seen the elasticity matrix for the plane strain problem. So this actually can be computed analytically without any bother. Now, this is a very simple element, and it can be derived without too many problems. The question is this element also a good element? historically speaking, this was the first element which was derived. The question is, how good is it? Is this a good element or not? And turns out that this is not such a brilliant element. It has some problems, and it has some problems in what is called bending dominated situation, which is pretty much what we have here in the figure. A test problem, the height of the cantilever is A, the length is 5 times A, and we have a moment applied here, a force coupled apply at the free end. Now, if we look at sigma x along this line, what we will have from our finite element solution is this: plus, minus, plus, minus, plus, minus, and so on. It should be 0. It's not. And it's not because the strains within an element are constant. So you will have an oscillating solution with plus and minus, plus and minus. It will arrange itself over something which in average will give us a 0, but within each element we will have either tension or compression. What is also bad is that the shear strain at node 2, the gamma xy computed from, say, from element 1, this should be 0. We have no gamma here. We have no shear strain here. But it's not. It's equal to V2 divided by A. If you go to the definitions of the strains, you will see that gamma xy from element 1 at node 2 is equal to V2 over A. This type of shear strain, which should be 0, but it's not, we will call it a parasitic strain, a parasitic shear, which will come and destroy the accuracy of our solution. So the element that we have here, historically speaking, it's the first element that was ever produced. The strains are constant. It will converge. It respects all the conditions for convergence, but is not such a good element. We will need a lot more elements on the height and on the length to get the stresses and strains right. And this comes also from the fact that we are using here, for instance, piecewise approximations. So constant, but to which point will this constant value actually be associated? Constant here, constant here, constant here. So the only way to reproduce the 0 is this oscillating situation. We might take lots of elements, say that we take 8 or 10 elements on the height, then we will have a much better approximation for our problem. But if we have such a mesh, then we are not doing too great. Okay. Let's take a break. And before we go on a break, let's hear some questions. Yes, I'm listening. There are no questions? Doesn't seem to be. Well,
questions.
Yes. Yeah.
In page of total potential,
Yeah.
some pages previous.
Yeah. Yes.
I just want to know in the first equation, the last term, it means the the potential caused by shear deformation, right?
No.
No.
The potential of an external force which is applied over the over an edge.
Over the edge.
Over the edge.
Over the edge.
If you look here.
Oh, sorry, I didn't see this
It's the
page.
potential of the external forces which is applied over an element edge.
Okay, I
Yeah?
understand. Yes.
This is internal forces. This is potential of external forces.
Yeah. Okay.
Okay. Other questions?
Yeah. Okay. So I would actually like to ask again about the thing that I'm asked about regarding the shape functions on page 26 and 27.
I don't have a numbering here.
Okay. It was
Here?
yes, and the next slide.
Yes.
The 1F. Yeah, those two. So this matrix we're looking at now, that is the derivative of.
Yes.
So it's a derivative of the shape function, I guess.
Yes. That is what I said. Here, we don't actually need to go through the shape functions.
Okay.
If you look at epsilon x, epsilon x should be equal to a2 because it's du dx.
Okay.
The other two terms will disappear. So a2 is minus 1 over x2 u1 plus 1 over x2 u2. We can put this directly in our B matrix. Minus 1 over x2, 0, 1 over x2, and then 3 more zeros. This line multiplied with a vector of nodal displacement will give me minus u1 over x2 plus u2 over x2, which is exactly this, which is actually my epsilon. So the thing here is that going through the shape functions, we can go through the shape functions. But going through the shape functions will mean a bit more work than going directly.
Okay.
Simply because these are the relationships between the strains, epsilon x, epsilon y, gamma xy, and some of the coefficients here. If I can determine these coefficients, then I have determined the strains. And then I don't need to go through shape functions. I know they need to be bilinear. It cannot be anything else, but I don't really need to know them. Do you see my point here?
Yeah, I think so, yes.
So, yes, we can, if you, just for the sake of it, if you would like to determine the shape functions for this, you can do it and see that you end up with the same B matrix as the one here. Here is just taking into account the fact that the problem is so simple that I don't need this extra step. This is not the case for the four-noded element. I cannot do anything directly there. I need to go through the shape function. And we will talk about this after the break.
Okay.
Are you clear on this topic?
Yes, thanks.
Yeah,
thanks.
it's just that it's simpler like this. Okay. Other questions?
Yeah, a question.
Yeah.
About the expression of u and v, why would there be no xy terms? I think that xy should also be in the first degree, and it should.
Yes.
A basic element.
Whether here or where?
Yeah, here.
Here. Why
Yes.
don't we have an xy term?
Yes.
What will happen if we don't have an xy term?
It's not constant along the.
No. How many constants we will need for the polynomial? So u of x and y, you are telling me that I chose the expression a1 plus a2x plus a3y. This is the expression I chose.
Yes.
You would like to have u of x and y, a1 plus a2 of x plus a3 of times y plus a4.
Yes, that's what I mean.
Yes. How would you determine the a4?
Oh, there is no way to determine that.
Yes.
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 That's-
So you have 3 nodes, which means 3 conditions. Yeah.
Okay.
If I have 3 conditions, at most I can determine 3 coefficients, which actually will condemn me to this approximation. I can't do anything better.
Yes, I understand.
It seems frustrating, doesn't it? I remember I had the same question as you did,
Yeah.
and it seems a bit frustrating, but that's the problem. That's the thing.
Okay.
Other questions? Always the degree of the polynomial is connected to 2 things. Number 1, which is the term of the complete polynomial I need to have in my approximation. In this case, with epsilon, with first order derivatives in the expression of the total potential, I need to have a complete polynomial of first order. Then, on top of that, I can start adding other terms. But I will be limited by the number of nodes that I have for my element. The number of nodes will give me the number of condition equations. If I have 3 nodes, then 3 condition equations that are then at most 3 constants. If I'll have 4 nodes, then I will be able to determine 4 coefficients, and I will take the x and y term. But more on this after the break. Other questions? If there are no more questions, then I will suggest that we take a break until 25 minutes to 12, so 12 minutes, and then continue after the break. Okay? Hear from you all in 12 minutes, 25 to 12. Let's proceed and look this time at what is normally called a bilinear rectangle, also denoted in the literature as the Q4 element. So 4 nodes. In this case, the approximation of u and v will contain an extra term, will contain not just the first 3 linear terms, will also contain a term in x and y. And we're allowed to do this, or we can do this, because simply because we have an extra condition equation from which to determine our 4 constants. Why do we call it bilinear? Because if you look at u and v, and if you take y, for instance, in the expression of u, both in the expression of u and v, if you take y as constant, then you are left with a linear interpolation in x. If you know, so along a line which has constant y, so along a line which is horizontal, constant y, then the interpolation in x is linear. If you have a constant x, so along any vertical line, the interpolation is y is also linear, but this time in y. Now, this is not as simple as the triangle, so we will have to go through determining the interpolation functions. We could do it, say, taking n1, the interpolation function corresponding to u1, and saying n1 needs to be 1 at nodes 1 and needs to be 0 at nodes 2, 3, and 4. And from that, we can determine the 4 constants involved in the form functions. Or we can do it like this. We can look at the interpolation of u along sides 1, 2, and along sides 4, 3. u12 is a minus x over 2a times u1 plus a plus x over 2a times u2. This is how the interpolation in x would look like along the line 1, 2. And u3, 4 would be a minus x over 2a times u4 plus 8 plus x over 2a times u3. These are very easily checked, assuming that your element has origo here. So node 1 has coordinates minus a minus b. This is a minus b, a, b minus a, and b. If you interpolate u12 along line 1, 2, then you have u1 and u2, and you need to have a linear interpolation between u1 and u2 for any value on this line. Once we have established u12 and u34, what we can do is look at an interpolation in y direction and base this interpolation not on nodal values, but on edge values. So at any position x here, if we interpolate along a vertical line, we will obtain u of x and y, which is b minus y divided by 2b times u12 of x, wherever this might be placed, plus b plus y divided by 2b times u34 of x. We know this, we know this. We substitute these two expressions in here, and we finally get our approximation for u of x and y is a minus x times b minus y divided by 4ab times u1, so this will be n1, a plus x times b minus y divided by 4ab times u2, and this will be n2, n3 and n4 will follow with these expressions. So now we know the interpolation functions for this element. The same interpolation functions apply for v, of course. U is the vector containing u and v, which is nothing else than matrix of shape functions times displacement at the nodes. And here in the matrix of shape functions, we arrange our 4 shape functions: n1, 0, n2, 0, n3, 0, n4, and 0, because these will have to multiply u1, u2, u3, u4, then 0 and 1, 0 and 2, 0 and 3, 0 and 4, because these will have to multiply v1, v2, v3, and v4. The B matrix, simply obtained by applying our differential operator to the matrix of shape functions. On the first row, we will have dn1 dx 0, dn2 dx, 0, dn3 dx, 0, dn4 dx, 0. Minus b minus y, b minus y, b plus y, minus b plus y. These are the derivatives with respect to x of the shape functions, n1, n2, n3, n4. Here, on the second row, we will have the derivatives with respect to y of whatever is on the second row. So 4 zeros, and then dn1 dy, dn2 dy, dn3 dy, dn4 dy. And here we will have dn1 dy plus dn1 dx, and so on and so forth. So this is how we compute the B matrix. The differential operator delta, d dx 0, d dy 0, d dy plus d dx applied to the matrix of shape functions. This is our matrix B. And K is, as we said, by the general formula, an integral over the volume of the element of B transpose EB. B is here, E is the strain, it's the elasticity matrix for plane stresses. We can perform an integral over the thickness. Nothing changes over the thickness. So once we perform this integral, we'll have the thickness here, the thickness of the element. And the integral will be reduced from an integral over the volume to an integral over the area of the element. And we have this one, which can be expressed as a series of two linear integrals, minus a, from minus a to a, from minus b to b, from this product. So what we do is that we compute the product. This will give us second order functions in x and y. Within each term, we integrate it from minus a to a, and then from minus b to b. And this is how we obtain the K matrix. Actually, because of the B matrix being so simple, we can compute the matrix K analytically. So we can compute analytically each term in the stiffness matrix. Now, let's look a bit at the performance of this element. The performance of this element is better than that of the triangular element, but it still has problems with bending dominated problems. If you take, for instance, a deformation in pure bending, so assuming that your element is subjected to pure bending, you'll have a bending moment here, bending moment of equal magnitude here. These are in balance, and the shear stresses are 0. Of course they are, there is no shear force, nothing here. So the shear stresses should be 0 within the element, and epsilon should be theta b times y divided by 2a. This will give you tension here, compression here, going through 0 at this point. So these are, if you want, the analytical solution. What does this solution presupposes? Well, if you look at how the edges are deformed, here the edges will stay undeformed, so there will be straight lines. Here, however, the edge will have a bended shape corresponding to our bending deformation. So this is how the edge will deform. What happens in the finite element approximation? We have bilinear approximations of the displacement. So we will be able to reproduce this deformation correctly, but we will not be able to reproduce within one element this curved shape of the edge. The only thing that our form functions can do is to predict a linear variation of the displacement V along this edge. And it will result to be 0. So at the end of the day, this is the real displacement. The approximation of the real displacement field within our element is like this, straight edges. What will that imply? Well, that would imply that epsilon x will still have the right expression, if you want. But we will also have a strain deformation, simply because in order to accommodate our form functions and the way in which we approximate the displacement, we need to change this angle. This angle cannot stay 90 degrees. This will be changed. And this is changed through a shear strain. It's the shear strain changing this angle so that the element can accommodate this displaced deformed shape. And this deformed shape is the only one possible because this is how we have interpolated, we have approximated our displacements. So we also have a shear deformation, which is theta element times x divided by 2a. From the point of view of the strain energy, this means that the work done by the moment, as these edges rotate, in our element, here it's stored just in bending. Here, the work done by the moment is stored both in bending and in shear strain energy. So this, the response of the element will be stiffer than the real situation. For M element to be equal to MB, then theta element needs necessarily to be smaller than theta B. Actually, we can compute this average. And what we see when we compute this ratio, the ratio between theta as resulting from the element analysis and theta as it should be, is 1 minus nu squared divided by 1 plus 1 minus nu divided by 2 times A over B squared. This parasitic shear, we call it parasitic because it shouldn't be there. This should be 0. It's not. So it's a parasitic term. This parasitic shear will make the element, the rotation for the element smaller than the actual rotation. What is to be noticed here is that this ratio also depends on the ratio between A and B. So the larger this ratio, the larger the error. Which means that from a practical point of view, what we have to conclude directly is that whenever we solve a problem using the Q4 element, the best alternative that we have is to assume very compact elements, so with A and B very close to one another. Situations where A is much larger than B will lead to extreme errors here. The parasitic shear strain will increase in such a way that we will lose a lot of precision in our analysis. So one direct conclusion of this theoretical aspect is that if we use the Q4 element, especially in bending dominated problems, then we need to make sure that our elements are very compact, as close to a square as we possibly can. Okay. Now, are these 3-noded and 4-noded elements the only ones at our disposal? And luckily, they are not. We can define the so-called linear strain triangle. In this case, we have 6 nodes. So we add a node at the mid sides of the element. 1, 2, 3 at the apex, and 4, 5, 6 at the middle of the edges, 1, 2, 2, 3, 3, 3, 1. In this case, we have 6 condition equations. So we will be able to accommodate a quadratic interpolation of u and v. We will be able to write a complete second order polynomial in x and y, simply because we will have enough constants to determine, enough equations to determine these 6 constants. 6 nodes means 6 condition equations, that is 6 constants here, complete polynomial of order 2 in u and of course in v. We can do the same thing for the 4-noded element. We can add nodes at mid-size. Then we will have 8 condition equations, and we will be able to accommodate a complete order, second order polynomial plus 2 extra terms, third order terms in x and y. So we will be able to accommodate also x squared y plus xy squared. Note here that whenever we add terms to a complete polynomial, we will strive to maintain the balance between x and y. So if we are adding the third order term x squared y, then the next term should forcefully be xy squared. Another thing that we need to note, we will not move to third order terms before we have a complete polynomial of second order. So first of all, a complete polynomial of second order, then we will see how many terms we can still add and what will the shape be. The shape should always be in such a way, if it's not a complete quartic, then the shapes should be always in such a way that there is balance between x and y. We can also add an extra element. This is called the serendipity element, the one with 8 nodes. We can also add a 9 node at the center of the element. And in this case, we will be able to increase here by 1 the constants. So we will be able to put y squared plus the x squared y squared in both u and v. Why would we do this? Well, we would do this because this will, if we take a second order polynomial to approximate u and v, then this edge, which will be deformed in a curved shape, will no longer need to stay straight by your finite element approximation. This deformed shape can be very well accommodated by this curve, by this second order polynomial. Now, what is the consequence of this? The consequence is that the element is very accurate even in bending dominated problem, and there will be no parasitic share appearing in the response of the element. So this one can be trusted for bending dominated problems. One word about consistent nodal loading. Two situation, a distributed force on the edge, we say distributed traction on the edge. Assume this is applied on the edge for 3, that is for y equal b. Then the approximation of the displacement on this edge would be 1 over 2a, a minus x, a plus x, times v4, v3. This is how the displacement of v along the edge 4,3 can be constructed. We simply insert y equal b in our shape functions, and we will determine the variation of v along the edge 4,3. We can assume that a linear variation for phi, or we can take a constant, or we can take a parabolic, whatever. If we take a linear variation, then we can use N34 to interpolate phi between Q4 and Q3. And then we will end up with vector of consistent nodal loadings as an integral from on the edge 3,4 of N34, this one, times phi, which is this one, times ds, which is the infinitesimal element along the edge. If we have a concentrated force instead of a distributed force, if we have a concentrate force here, then we can simply take the value of the displacement at this point and multiply it with the force, and this will give us the consistent nodal loading. How do we obtain this? Well, we take the coordinates of this point, substitute in the matrix of shape functions, and that is the value at that particular point. If we do this, if we actually perform all these integrals, we end up with the following set of consistent nodal loadings. This one gives us this, and this one gives us this. You can also check for your own curiosity that this is what comes out of the integration here and the value of the shape functions at this particular point. Again, these forces, consistent nodal loadings, are work equivalent, so energetically equivalent and statically equivalent to the actual applied loading. Now, let's say something about stress evaluation. So how do we proceed? Well, we have the stiffness matrices for all the elements. We assemble the structural stiffness matrix. We impose boundary conditions and determine the displacement vector D. We then go back at element level and we make a loop over all elements. And for each element, we extract the particular nodal displacements which are related to that element. So for element 1, for instance, we extract the displacements corresponding to nodes 1, 2, and 3. For element 2, from the large D vector, we take the values corresponding to nodes 2, 4, and 3. Within the element, we define a number of locations where we want to evaluate the stresses. And for a certain location, we will compute the B matrix at that particular location, x, y, and y, say at the centroid of the element. Multiply it with a vector of nodal displacement and get our epsilons, epsilon xy and gamma xy. We then multiply this by the elasticity matrix and get sigma x, sigma y, and tau xy. So this we do in the case of the triangular element. The stresses are constant, so we might say they are associated to whatever point we want. For the four-noded bilinear element, we have the B matrix, which is a function of x and y. So actually, we need to choose what is the point where we would like to evaluate our stresses in. We'll see that there are rules about how we choose these points a bit later on in the course. What we should note here is that along the edge 2, 3 in this arrangement, the stresses and the strains and consequently the stresses are discontinuous. Which actually means that if we take, for instance, node 2, and we use element 1 to determine the stresses in node 2, and then we look at the same node, but this time we use element 2 to determine the stresses at node 2. The two results should be equal, where they are not. Sigma x at node 2 from element 1 is not equal to sigma x from element 2 at node 2. Sorry. So sigma x from element 1 at node 2 is not the same as sigma x at node 2, but computed from element 2. So what do we do? Well, one solution that is very used is that we simply take the average value. We add these two, divide by 2, and we say sigma x at node 2 is this value. Whatever we compute from element 1 plus whatever we compute from element 2 divided by 2. That's one way of dealing with the discontinuity. Many commercial codes do have this as a default option. Now, we've been looking at plane stress situation. How about plane strain situation? Well, the only thing that changes in a plane strain situation is the expression of the elasticity matrix. So once you have the B, instead of using the plane strain E matrix, you use the one corresponding, the plane stress E matrix, you use the one corresponding to plane strain, which is this one. Everything else stays just the same. It's just the expression of the E matrix that changes. What happens if we have volume elements? We simply add an extra direction. So we simply put the sigma theta and the taus that are missing, and we get three-dimensional brick elements. The extension is very well presented in the book. It is absolutely trivial. It's just adding one extra dimension to what we have discussed for plane stress and plane strain problems. The properties of the elements stay the same. The 8-noded brick element will be bad in bending for the same reason as the 4-noded plane stress, plane strain elements are bad in bending, and so on and so forth. And then we have another type, more special type of 2D elements, the axis symmetric elements. Here we need to make sure we understand correctly how this element is defined. The nodal points are no longer points in themselves. They describe nodal circles, like here. And we take a chunk of the element, instead of taking as for the plane strain, thickness equal to 1, we take an angle here at the center which is equal to 1 radian, and we perform the integrals. Very much like the 2D elements, but this time it describes a situation where everything is axis symmetric. Having said that, I think I will stop here and wait for some questions. Okay, do you have questions? As I understand, there are no questions. So, given that there are no questions, we will set a point here, and I will end my lecture. Have a nice day, and please stay healthy. Bye-bye.